Okay, great. So we should be recording now. So this is section 7.5, and we're looking at number 15, solve each exponential equation for x, show complete work, and check your answer using a graphical process and a numerical one. Find your answer in both exact form and rounded form to 3 decimal places. So they want us to solve these algebraically and graphically. And when they say numerical one, that's basically using the intersection routine, okay, on our calculators, all right? So let's get the pencil going here. So I can write on here. There we go, it's my pencil. Okay, so let's go do the algebraic approach first. So we need to solve for x, all right? So the way to do that is to rewrite this, excuse me, as a logarithmic equation.
Okay.
Okay, so that says the exponent on a base 2 that gets me 12 is equal to x. So that's the whole thing from the last module about being able to convert back and forth between logarithms and exponentials. So if you're given an exponential, you should be able to turn it into a logarithm. If you're given a logarithm, you should be able to turn it into an exponential.
Okay.
Okay, so far so good. All right, now we're going to go one step further here, and we're going to solve this or rearrange this into something we can put into our calculator using the change of base theorem. And the change of base theorem says that if you have logarithm base b of, let's say, a, then that's going to be the common log of a divided by the common log of b. Whereas what it does is it lets you convert any logarithm in any base into base 10. Or we've been working in the discussion question with base e, you can convert it into base e also. But the textbook does base 10, so let's stay with that. So the way I remembered this, the way I got my poor frail brain to keep it straight, was I remembered that the number that was already superscripted, that was in the lower position in the original logarithm, was the one that went in the denominator. And the one that wasn't in that position went in the numerator, okay? So it's sort of lucky. It kind of works out the way you would hope it would, okay? All right, so let's come back here and do that on this one. So that's going to be common log of 12 divided by common log of 2 is equal to x. All right, so time to get the calculator out, because if we want to get the exact form and an estimated form out to 3 decimal places, then we're going to need the calculator for that. So what we're going to do here is we're going to come in, clear out this craziness from previous problems. We're going to go log of 12 divided by log of 2. All right, so what that number is, that's the exponent that if I take 2 and I raise it to that exponent, I will get back 12. So just a quick aside, we'll only do this once for this one to just kind of verify it. That number right now is stored in this variable called ants. The last thing you did always gets stored into ants, okay? So notice ants is 3.5849 blah, 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 right?
Yeah.
So if I take 2 and I raise it to that number, which is ants, and I hit an enter, I get back 12. Okay, so that's what that number is. It's the exponent on a 2. Then when I take 2 and I raise it to that exponent, I get back a 12. Okay? All right, so let's come back over here because they wanted the out to us here 3 places. So to 3 decimal places, it's going to be 3.585. So 3.585 is approximately equal to x. Okay, so this one right here, this is the exact. This one right here, this is the approximate. And they made a big deal in the book to explain the difference between those two. Mathematicians are geeks. They like the exact answers, okay? But out there in the real world, you're going to use decimal approximations. And by the way, that's also a perfectly acceptable exact answer also, the log base 2 of 12. Okay. All right, now they also wanted a graphical solution to it, so we need to go get the graphical one. So to do that, we go back to the original equation, and we clear out what is in y1, we clear out what is in y2, and we'll put 2 raised to the x into y1, and we'll put 12 into y2. So knowing a little bit about what I know about horizontal lines, I know y equal to 12 is going to be a horizontal line passing through 12 on the vertical or y-axis. So I know I'm going to have to go in and adjust my window here. Let's do a zoom and a 6 to begin with. I'm going to have to adjust my window a wee bit to see that second graph. Notice it's up here. It's up, excuse me, in the neighborhood of 12. So if I press my window, instead of going from -10 to 10, -10 to 10, I'm going to go -10 to 10, and then from -10 to 15, so that I'll see that horizontal line in there. And so with those window settings, when I press graph this time, I see the point of intersection between my two graphs, okay?
Mm-hmm.
All right, so they want us to make a sketch of that over here in our homework, so let's do that. Doesn't have to be anything fancy, just so that it's representative. There's my increasing exponential. There's my horizontal line. That's the x-axis. That's the y-axis. And then we want to know, what is that point right there? What is the point of intersection? I know the y value is 12, but I need to know what the x value is. So to do that, I'm going to go second, calc, number 5 for intersect. The little Frogger guy as close as I can here. We'll go first curve, second curve, best guess. And oh, look at that. We got the same number, right? Okay, so that means x, again, is approximately equal to 3.585, rounded out to 3 places. Okay, should we do another one?
If you want.
Well, okay, let's do it. Let's go do part B. Okay, so in part B, again, we've got an exponential equal to a constant. And so to be able to solve that, we're going to go in and use the logarithm to rearrange this. And we're going to say, okay, the exponent on 1.23 that gets me 27 is equal to x. So using change of base theorem so that I can actually evaluate that on my calculator, that's going to be log of 27 divided by log of 1.23 is equal to x, all right?
Mm-hmm.
Okay, so on the calculator, if we go get out of this, let's go to second quit. So I'm going to go log of 27 divided by log of 1.23. Dread, I forgot to close my parentheses. So start over. Log of 27 divided by log of 1.23. Always remembering to balance my parentheses and put the closed one in there. And I get back a decimal approximation of 15.921 out to 3 places.
Okay.
So 15.921 is approximately equal to x. Okay. All right. So if I was going to do this graphically, go back into the calculator here. Go to my y equals, and I'm going to change this to 1.23 raised to the x. And I'll change this to 27. Okay, now just as before, we noted that was a horizontal line passing through 12 on the y-axis. This time we're going to pass through 27. So I'm going to have to adjust my window again. In particular, I'm going to have to adjust that y max to, let's say, 30. That should be plenty. As long as it's bigger than 27, okay? And so I press graph. And I go, oh, fuzzy feathers, because it's over here. It's further over in quadrant 1 than I was giving it a window for. So I got to go back and do some more adjusting here. So let's go back into window. And my x max isn't big enough. So let's make my x max. Let's start off with 30, just to see if that works. So I made my y max 30. Let's make the x max 30, right? Yeah, looking good. Yep, I'm going to see the point of intersection, okay? So let's come over here and make a representative graph on my homework. So it looks something like that. And there's my point of intersection. There's my x-axis. There's my y-axis. Really a good habit to get into, although the book doesn't make a big deal out of it, is you really ought to write down the endpoints of your axes. So if you have to go back and recreate this graph, you have all the information you need. You got the x-min, you got the x-max, you got the y-min, you got the y-max. So you can go back and make the graph again if you need to. Okay, so the value of x we're looking for is right there. So we're going to go second, calc, number 5 for intersection, first curve, second curve, best guess. And oh, look at that, amazingly enough, we got the same answer again, okay? So again, that's going to be x is approximately 15.921. Now, if you don't get the same answer over here when you did the graph as you did when you did it algebraically, then you did one of the two of them wrong. And so you need to go back and check and see what went crazy there, okay? All right, let's go do part C. Now, part C, they added a little twist. And that notice that parts A and B, hey, Jamie, how you doing? Parts A and B, notice that there was an exponential set equal to a number, an exponential set equal to a number, right? Okay, well, in part C, there's something multiplied times the exponential. If you thought about this in terms of our applied problems that we did back in the previous chapter, this is like the initial amount. That's our A. It's A times B to the x equals, some number. So you need to get that number out of there. It's got to get out of the way in order before we use the logarithm. So our first job is to divide that out. So I'm going to divide both sides by 5. And if I do that, I end up with 4 to the x is equal to 5. And now that's looking remarkably like the problem that we did in A and B. It's got an exponential set equal to a number. Okay, so how do I get x out of the exponential position? Well, we use the logarithm. Because remember, the logarithm and the exponential are inverse operations to each other. And so the way you read it is you say, okay, the logarithm on base 4 that gets me 5 is equal to x. And technically, you've done the exact answer at that point. But if I want to get a decimal approximation of it, I'm going to use the change of base theorem. Now, I'll show you in a minute, if you've got a newer calculator or you're using one of the apps, there is a way to input this directly into the calculator. The calculator will let you put in log base 4 or 5. But the older, like TI-83s, don't let you do that. And there's other reasons to no change of base. So we're gonna do it by change of base, okay? So using change of base, that's going to be the logarithm of 5 divided by logarithm of 4 is equal to x. And again, how I keep it straight in my head is I say, well, look, the number that was subscripted in the original is the one that's got to go below. It was already the lower one to begin with, right? The number that wasn't subscripted, hey, that's the one that's going in the numerator, and I'm going to use common log for both of those. All right, so to the calculator. So I'm going to get log of 5 divided by log of 4. And I get back the decimal approximation out to 3 places of 1.161. That's approximately equal to x. So again, that one is the exact. And this one right here is the approx. That's the approximate, okay? So in the instructions, when they ask you for the exact one and the approximate one, this is the exact, and like I said earlier, that one also is exact down there. Okay, let's check this bad boy just to make sure that it was right, okay? So what we're saying is that 5 times 4 raised to this exponent gives us back 25. So remember, that number is stored in ants, right? In other words, the 1.1609694.4 is in ants. So if I go 5, parentheses, 4 raised to the ants, to the ants. There we go. You get back 25. So it indeed works. Okay. All right, let's go do the graphical solution to this. And so we're supposed to put in 5 times 4 raised to the x into y1 and 25 into y2. Okay, well, I know that the horizontal line going through the y-axis for y2 is going to go through at 25, so let's just go ahead and try the window settings we had from the last one. Let's see how it works. Pretty good, other than I got way too stinking much x-axis in there, right? So let's go clean that up a little bit. Let's make this go, I think -5 to 5 is going to work. Particularly, I know that because we go to 1.16, right? So changing my x min to -5 and my x max to 5 is going to make it a lot easier to see the point of intersection. Yeah, much better. Muy bueno. Okay, so let's go to second calc. Number 5, first curve, second curve, best guess. Oh, and look at that, I got the right answer again. I'm so stoked. Okay, I must teach this or something. Okay, so again, it's a good idea in case you have to come back and recreate this to put your window settings on the ends of your axes, okay? And I see that x is, again, approximately 1.161, okay? All right, one more in this one. The thing to notice this time is it's not a number being multiplied by exponential, but we've got a number added to our exponential. So again, what we want to do is get the exponential by itself and get all the rest of the stuff away from it. So we're going to go ahead and subtract 4 from both sides. And so if I subtract 4 from both sides of this, I get 3x is equal to 4. Right? Subtract the 4 from the 8 and I get back a 4. Yeah? Mm-hmm. Jamie's all good? You hanging tough? Okay. All right. So now what? So now use the definition of the logarithm. So the exponent on a 3 that gets me 4 is equal to x. Okay, so I'm going to try and see if I can show you how to use the cool function on the calculator here. So it turns out that these green things here, this F1, F2, F3, F4, if you have one of the newer calculators, those are your function keys. And so if you hit alpha, and then you hit the window key, you see option 5 there is log base. In other words, it'll let you do the log base. So if your calculator is a newer one, it'll have that built into it. So if I grab option 5 here, I can put in log of 4, comma, base 3, if I remember correctly. I'm hoping I remember right. Let's see if I was right about that or not. I can always check it. I can go 3 raised to the ants, and if I get back 4, yep, then I did it the right way. So my hardest problem with the really new ones don't do it like that. They actually make it look like a logarithm. You know, mine's a sort of new one, so it doesn't quite have it as pretty to look at. But what it's saying is that the first number is the argument, the second number is the base. Okay. All right, but that said, can always use change of base. Can always go log of 4 divided by log of 3. It'll get you the exact same answer, all right? So in this case, it's 1.262. So that's my approximate x. Now, I'll let you guys do the graphical part on your own. Well, no, actually, let me do the graph one with you here. I shouldn't skip that. This one's got a little bit of a twist to it. Okay, so hit our y equals. So this time we got to put in 4 plus 3 raised to the x. And then in the second one, got to put in an 8. Don't know any better, so I'm going to do a zoom and a 6. Let's do a zoom and a standard. Okay, hang on. Yeah, no, hang on. Put in an 8, not an 85. Let's try that again. There we go. Cool. Because notice what happened here is this 4 shifted up our horizontal asymptote up to 4. In other words, the stock graph, if I was just to look at y equals 3 to the x, would look something like this. And from the last chapter, we know that the x-axis here is playing starring role of a horizontal asymptote. So what this 4 did is it simply shifted that horizontal asymptote up by 4 units. So if this one here was y equals 3 to the x, this one here would be y equals 4 plus 3 to the x. In other words, the whole thing got moved up by 4 units. Okay? All right, so let's go back and take a look at the graph. Let's do a second, do a calc, do number 5 for intersect, first curve, second curve, best guess. Hey, and we got the same answer again. Life is good, all right? So that answer right there was x is approximately equal to 1.262. That's my x-axis, that's my y-axis. In this case, I want negative 10 to 10, and I want negative 10 to 10. Okay, any other questions on those? Is okay? So I think I've pretty much butchered 15. Sliced, diced. Mounds and mounds of Julian fries, right? Okay, so now what happens in 16? Well, they said, let's do it all again, but let's make them harder. So now they give us some tougher problems. So they're just kind of upping the ante a little bit here, all right? So same idea. You need to put them into exact form and then round it off to 3 places, and they want to see the graphical solution. All right, so a big hint from problem 15 is that notice that once I got it looking like this, in other words, once I've got it looking like a to the x is equal to b, then I simply have to bring out the logarithm and I've got it solved, all right?
Mm-hmm.
So in 16, you need to do some algebraic steps first to isolate that exponential. In other words, you need to get it to look like a to the x is equal to b. So you can think about, change color here for just a moment. You can think about this thing, the exponential part there, as just think about that as that's the big blob I need to solve for. And I need to get that isolated. I need that all by its lonesome. So to do that in this case, I'm going to go ahead and first of all subtract 8 from both sides. And if I do that, I'm going to get negative 2 times 6.2 raised to the x is equal to negative 18. Is that okay? Okay. All right, now I'm going to come through. I'm going to divide both sides by a negative 2. And if I divide both sides by a negative 2, that's going to get me 6.2 raised to the x is equal to a positive 9, right? Because a negative 18 divided by a negative 2 gets me back a positive 9. So far, so good?
Mm-hmm.
All right, yay team. Got an exponential equal to number. The exponent on base 6.2 that gets me 9 is equal to x. So what that says is that logarithm of 9 divided by logarithm of 6.2 is equal to x, okay? And I'll let you do the decimal approximation part. I'm just going to go show you the calculator part here real quick.
Okay.
So going to my y equals, clear that out. And let's see, what was it again? It was, oh, come on, you. It was 8 minus 8, subtract 2 parentheses, 6.2 raised to the x power. And then down here was negative 10. All right, so if I do a zoom and a standard, I sort of see the solution here, but I probably ought to do a little bit more y min, right?
Mm-hmm.
So let's go back over here and let's take y min to say negative 15. All right, cool. So coming over here, I'm going to make a reasonable, that wasn't very reasonable. Let's try a straighter line than that. I'm going to make a reasonable copy of the graph onto my homework paper. That's my point of intersection right there. That's the value of x that I'm looking for. Negative 10 to 10 and negative 15 to 10 were my axes. Okay, so let's come in to the calculator, go second, calc. Go to number 5, first curve, second curve, best guess. And my decimal approximation of this point right here was at about 1.204. So that's approximately x is approximately 1.204. And I bet you if you do the change of base and do the actual calculation over here, you're going to get the same thing. All right, let's move on to part B. All right, so it is an exponential. Just the exponential happens to have a sum in it, so there's going to be a little bit of a twist at the end with the logarithm evaluation, but no big deal. We have the technology. We know that the exponent on a 3 that gets me 18 is equal to 2. Yeah. Sorry about that. Equal to x plus 2. Sorry about that. I was dropping off the x there. What was I thinking? Okay, so now the next thing I've got to do is to solve it for x is I got to get that 2 off of there by subtracting 2 from both sides. So logarithm base 3 of 18 minus 2 is equal to x. Is that making sense?
Yeah.
Yeah, you sure? Brittany, it's good. Jamie, it's good.
Yeah, it's good. I did it different, but got an answer. So
Let's see if we get the same answer, okay?
okay.
Let's see, all right? Okay, so from here, at this point, I'm going to go ahead and use change of base here on it, right?
Mhm.
So if I use change of base on here, this is going to be the logarithm of 18 divided by the logarithm of 3 minus 2 is equal to x, okay? So let's go get our decimal approximation here. So we got logarithm of 18 divided by logarithm of 3 minus 2, and that's our decimal approximation right there. Jamie, did you get that for the decimal approximation?
Yeah.
You did?
Uh-huh.
Cool, all right. Sweet, so what did you do different than I did? What did you do?
So I just left the so I basically did like the inversion. So I said logarithm 3 of 18 equals x minus 2.
Equals x minus 2?
Mm-hmm.
Oh, yeah. Yeah, that's not quite right. That's
Right.
that was luck.
I know. It felt really fumbly when I was doing it, so I didn't think it was right.
Yeah, you got lucky, you got the right answer, but well, that doesn't quite work. Yeah, no, yeah, pretty much have to write it the way I wrote it.
Yeah.
Okay, if you guys don't mind, just interest of time, because we've got a lot to get through, I'm gonna let you guys do the graphical ones on your own, okay? Is that okay?
Yeah.
Okay, I think those are pretty straightforward, so. Okay, let's go do part C. And so in part C, again, we've got to solve for the exponential. So we're going to divide both sides through by 6 first off. So just going to come through here and divide out the 6 from both sides. And we're going to get 2 to the x minus 2. Let's make that look more like a 2. There we go. Is equal to what? 4, right? Okay, so the exponent on a 2 that gets me 4 is equal to x minus 2. So I'm going to add 2 to both sides. So the exponent on a 2 that gets me 4 plus 2 is equal to x. Now you can use the calculator on this one, or you can think about it. What's the exponent of 2 that gets me 4?
2.
Yeah. So this is 2 plus 2 is equal to x, or 4 is equal to x. Because this part right here, if you're sort of feeling comfortable with logarithms, that one I can do in my head.
Mm-hmm.
If not, don't worry. Do it on use the change of base theorem on it, okay? I mean, if we go in and we use the change of base on there, if we say, okay, logarithm of 4 divided by logarithm of 2, lo and behold, you get back 2, right? And that's fine. That's perfectly cool if you use the calculator on it. Okay, again, I'm gonna let you guys do the graphical part on your own, all right? Can't take all the fun from you. Got to leave you some fun to do, right? All right, so let's take a look at part D here. So again, we want to get the exponential part isolated, so we're going to subtract 5 from both sides. So we've got, I'm going to put that back to blue. So we've got, subtracting 5 from both sides, we've got 4 to the 2x is equal to 63. So that's 68 minus 5, right? Okay, so that says that the exponent on a 4 that gets me 63 is equal to 2x. All right, so like back up on the previous ones, here I had to add 2 to both sides. I mean, I had to do something to get x isolated by itself. Same thing here, I got to divide both sides by 2. So divide this side by 2, divide this side by 2. Let's try to make that more like a 2 there. There we go. All right, cool. So the decimal approximation can be calculated by going log of 63 divided by log of 4, all of that divided by 2, and that's, well, at the moment, that's the exact, that's equal to x, but we're going to use that to get our decimal approximation. So let's go ahead and do that. Okay, so we've got log of 63 divided by log of 4 divided by 2. So that's our decimal approximation right there, okay? 1.494 out to 3 places. Can I stop there at this one, or do you want me to do any more with it?
It's fine.
All good? Okay, cool. I'll let you finish it up from there. All right. Woo. Okay, we're finally to number 17, right? Okay, complete the work for all parts of the problem's right answers in exact form and in decimal form, rounded to the nearest hundredth. Suppose an investment is growing at a rate of 8% per year. Determine the doubling time for this investment if the starting value is the following, okay? All right, so first off, let's just do a quick reminder, okay? If we have A, where the amount is equal to, I'm trying to remember the notation that they use. Let's stay with Y. Let's just stay with Y for the moment, okay? So if we have Y is equal to A times B raised to the X power. A, that's the initial amount, right?
Mm-hmm.
B, that's the growth factor. They give us the growth rate, so we have to make that what, 1.08, right? Mm-hmm. Okay. And then X would be the time and Y is going to be the amount. All right, now if you're talking about doubling, right, if we're working with a doubling time, if we want to know the time to double, then that means we just have to take this amount that they gave us and we just double it and put it over here. In other words, it would be 2A is equal to A times B to the X, right?
Mm-hmm.
It's double that amount, right? So now notice that if I divide out A from both sides of this, right, I get 2 is equal to B to the X. And so you can get to the doubling time equation pretty quick if you do that. I'm gonna actually put the double in there and divide it out for a couple of them to see it. But you start to get the hang of it. You realize it's always going to be a 2 over on the left-hand side, okay?
Mm-hmm.
That's just going to happen every time, right? Okay, so the growth rate is 8%. So what that means is that the growth factor is 1.08, right? So double of this initial investment well, that's equal to 2,000, isn't it, right? So that says solve 2,000 is equal to 1,000 times 1.08 to the t. Yes, no, maybe?
Yes.
Okay, cool. All right, so first step, just like we were doing in the previous problems, we divide out the 1,000 and we get 2. 2 is equal to 1.08 to the t, which says the exponent on 1.08 that gets me 2 is equal to t, isn't it, right?
Mhm.
Okay, all right, so let's go ahead and do that. Let's use change of base on that. And so that's what? Log of 2 divided by what? Log of 1.08, right, is equal to what?
T.
To t, okay? All right, so let's clear this out and let's go ahead and go okay. So we get log of 2 divided by log of 1.0, there we go, 0.8. Close parentheses, hit an enter, and it's, basically 9 years, right?
Mhm.
It says round to the nearest hundredth. This is tenths, hundredths, so round to the nearest hundredth is 9.01 years, okay? So t is approximately equal to 9.01. What do you think? Is that okay?
Mhm.
Yeah? Jamie, so all good?
Can you just go over one more time, like why you did 2 equals 1.08t?
I mean, how did I get from here to here?
Yeah.
Okay, cool. No worries. Yeah, that's really critical that you understand that part. So it's good that we stop for a second and make sure that makes sense. So let's go back up for just a quick second. Let's go back up to these up here. So notice back up here in part D that I had to divide out a 2 from both sides to solve it, right?
Mm-hmm.
Okay. Or back up here in part C, I had to divide out that 6 from both sides, right? Okay. So it's kind of the same idea, is that I need to get the exponential isolated in this case. It's actually more akin to part C here, okay? And that I got to get that 6 off of there. I got to get rid of my starting or initial amount out of the way. So what I did is between this step and this step is I just came in and I said, let's divide both sides by 1,000.
I see. Okay, I got you.
And when I do that, I end up with a 2, don't I?
Yes.
No, I'm really glad you asked me that because that's a critical step. If you don't see that, then none of the rest of this is going to make any sense.
Right. Okay.
All right. Okay, so let's go on to the next one. So what's the double for 3,300?
6,600.
Yeah, 6,600, right? Okay, so that says 6,600 is equal to 3,300 times 1.08 to the t, right? Yeah?
Yes.
Okay. All right, so Jamie, check it out. Here we go. So what do I end up on the left-hand side?
2.
I get a 2, don't I, right? Yeah, that's got to happen every stinking time. What? These guys, what were they? Oh, they're messing with my head. 'Cause, yeah. Look, I got the same stinking equation again, didn't I, right? See, look.
Yep.
Yeah, no good rotten Bon Julios, right? Trying to mess with us here, okay? So now what? I'm gonna get the same freaking logarithm again too, aren't I? Log 1.08 exponent on a base 1.08 of 2 is equal to t, right? And if you think about it, it starts to make a little bit of sense, because what you really want to know is you want to know what turns that into a 2. because that's 2 times the initial amount, isn't it, right? Okay. And so it's always, in this case, it does not matter what your initial amount is. The time is always going to be 9.01. Okay, so in every one of these, t is approximately 9.01. So at this point, seeing as you have cleverly discovered their ruse, right? I mean, I'm being flippant. Okay, we do have to show one little thing. Okay, you got to show them this. Got to show them that those equations are going to be the same in every one of them. Okay, because I think they did say you have to show all your work, right? Yeah, show complete work for all parts of this problem, all right? Because they want to be mean to us. Okay, comparing your answers in A through D, what happened? They're all the same, right? And why is that? Well, because no matter what you start out with for the initial amount, you're always going to end up with that equation. Because when you divide out, when you divide out the initial amount from double the amount, you're always going to get a 2 on the left-hand side, okay? So I'll let you put in that part. You need to say something about that so that makes sense. Is okay? Can I move on?
Mm-hmm.
Okay, let me check my hit list here. Yeah, 18, okay, I need to do 18 also. Yeah, okay, cool. 18 is the last one from the practice problems, and then we can go talk about other stuff because I have quite the list to get through tonight. Okay, so show complete work for all parts of this problem. Write answer in exact form and decimal form, rounded to the nearest hundredth. Okay, so the body metabolizes caffeine at a rate of about 14% per hour. Excuse me, determine the half-life of caffeine in the body if you consume 1 can of Coke, which contains about 40 milligrams of caffeine, okay? All right, so that's our decay rate, right? They gave us the metabolizing, it means it's decaying at 14% per hour. So our growth factor is going to be 1 minus 0.14, right?
Mm-hmm.
So 1 minus 0.14, that's going to get us back what? 0.86, is that right?
Yes.
Okay. So that's our decay factor. It's not our growth factor in this case. It's our decay factor, okay? All right, so determine the half-life of the caffeine in the body, okay? So a can of Coke Zero contains 40 milligrams of caffeine. So 40 milligrams is your initial amount. So that's 40 times 0.86 raised to the t, right? Now, and we want to know the time necessary for this piece basically to become 1/2. So in other words, what time does it take for this to become 20? In other words, how long have you got until you've only got 20 milligrams of caffeine left in your body, right? Is that making sense?
Mm-hmm.
Okay. All right, so we divide out the 40 from both sides. If I do that, if I divide 40 from both sides of this model here, notice what ends up happening is we get 0.86t is equal to 1/2, don't we? So far, so good?
Mm-hmm.
Okay, cool beans. All right, so let's turn it into a logarithm. So the exponent on 0.86 that gets me, I'm gonna, if you don't mind, just make my life simple and make that 0.5 for the 1/2, okay? Is equal to t. Is that okay? What do you think? Yeah? Okay, cool. So you guys got quiet, so I want to make sure it's all right. Okay, so got the calculator out here. So using change of base, that's going to be logarithm of 0.5 divided by the logarithm of 0.86 gets me back 4.59 hours. Let's see, I forget how many places they want us. Nearest hundredth, okay? So we got to take it out 2 places. So 4.60, okay? So T is approximately 4.60 hours. What do you think? Does that make any sense?
Mm-hmm.
Okay, cool beans. All right. So you got a cup of coffee, which contains 100 milligrams of caffeine. So that means you got 100 times 0.86 raised to the T is equal to 50, right? Because what we want to solve now, again, we're solving for the half-life. How long until we've got half of the amount of caffeine in us, right?
Mm-hmm.
Okay, so half the amount of caffeine, if we start with 100, would be 50. Right, so if I divide out 100 from both sides, oh, wait a minute. Wait, yeah, I got the same equation again. These guys are just kidders, aren't they? Right? And so we're going to end up with what? We're going to end up with the same thing again. We're going to get logarithm of 0.86 of 0.5 is equal to my T, right?
Mm-hmm.
Which tells me that T is approximately 4.60 hours. So the half-life, if your body is eliminating 14% per hour, right? Then that means 86% of its remaining. The half-life doesn't change at all based upon what you've consumed. I mean, obviously, if you consume more, it's going to take longer for it to get out of there, because notice, with a can of Coke, we had 20 milligrams in 4 hours. With a cup of coffee, we still had 50 milligrams with us in 4 hours, right?
Mm-hmm.
Okay. And so with a can of Monster, which, God forbid you drink that nasty stuff, right? That's got 160 milligrams of caffeine in it. It's going to be the same thing again, isn't it, right? It's still going to come out to what? 0.86 to the T is equal to 1/2. That part's not going to change. And so again, you're going to get T is approximately equal to 4.6 hours, isn't it, right?
Mm-hmm.
Okay, again, compare your answers A through C. They're all the same. I'm going to let you write up the words on that, okay? But make sure you explain why that makes sense to you. I'm going to leave that part to you. I can't spoil all your fun. Got to give you some fun stuff to do, right? Okay, I think that's the end of the practice problems that I got asked to cover. Let me check on my list here. Okay, yeah, that's okay. Yeah, yeah. Yeah, I got 3 people who asked for those. So at least help 3 people, right? Okay. Oh, okay. I got to back up. Problem 6 on page 258. 258. Okay. Oh, okay. All right. Yeah, let's do this one. Okay. This is problem 6 on page 258. It says, use the table below to determine what 2 integers the logarithm lies between. Okay. So what they're doing is they're asking you to try and get the idea of the inverse relationship between logarithm base 2 and 2 to the x, okay? So let's go through the worked example first, so hopefully that makes sense. Okay, so if the value is 14.23, right? Where are they getting that? I'm a little confused. I'm confused.
So basically what they're saying, the values that they're giving you on the left-hand side,
Yeah.
because it's in between 8 and 6, it lies between those outputs. So then you make the logarithm form.
Oh, yes,
and the
I'm sorry.
input
Yes, I'm being
above it,
dense.
yeah.
That right, I get it. That 14 is between 8 and 16. Yeah, thank you. Yeah, sometimes the brain doesn't fire quite as fast as I want it to. Yeah, so 14 is in this interval between these two, right? Which means the logarithm's got to be between 3 and 4. So 2.7 is between 2 and 4, right?
Mm-hmm.
And so the logarithm's got to be between 1 and 2. Okay. And 9.45, that's going to be the same thing as it was for 14.23, right?
Mm-hmm.
That's going to reside between 8 and 16, which means that it's going to go between 3 and 4. Let's see, 0.2. 0.2 is going to be between 0.125 and 0.25. So logarithm base 2 of 0.2 is going to be between -3 and -2. Because the 0.2 fell between there, so the logarithm's got to fall between there. And then the 0.73, that's going to reside between 0.5 and 0.1, which means that the logarithm's got to reside between -1 and 0. Okay, I think we've got enough of this that hopefully whoever we're asking that one can probably figure it out from there.
Mm-hmm.
So I think I'll stop there because I really want to spend some time on the discussion question before we log off. Yeah, I just want to check. The vector problems base E question number 4. The video showed me how exponential with example can solve was. Okay, so this one I think comes partially from the discussion question. So I think we want to go over to a whiteboard here, okay? So let's do that. So it looks like what the question is this, is that we're given ln, no, let's make that clean, let's do it ln. Given ln of 3x plus 6 is equal to 5, and asked to solve for x, okay? So the thing to remember, and this is kind of an important ditty, is that logarithm of x, when you just see that, that's logarithm base 10 of x. And when you see ln of x, that's logarithm base e of x, where e is approximately 2.717 ... Okay, it's a number. It's like pi. It's just this amazing number that shows up in so many places in the real world that it gets its own logarithm. Bless you, Brittany. You got that nasty cold that's going around?
I don't know. My throat is kind of sore, and I don't feel so great, but I'm hoping not.
Oh, my condolences. My wife came down with it Sunday, and my daughter just came down with it yesterday, and it's not pleasant.
Yeah, I heard.
Yeah, lots of hot tea and a hot bath, and saline rinses for your nose. That's what's been kind of keeping them moving. Bummer. I hope you don't have it because it's not fun.
Yeah.
Okay, so if you take a look at the calculator, you'll notice that there are 2 logarithm keys in your calculator, one for base 10 and one for base e. They're built into the calculator. And if you try to remember which one is which, notice the second function on the logarithm is base 10, right? If you go second logarithm, it gives you a 10 to the x, doesn't it, right? Okay. And if I hit a second ln, oh, it gives me an e to the x, okay? So yeah, they would give you a built-in cheat sheet to remember which one is which, right? So log is base 10, ln is base e. All right, so back to the problem at hand. They want us to solve this one, all right? So since this is base e, what you can do, if it helps, is you can rewrite this as logarithm base e of 3x plus 6 is equal to 5, okay? Now I'm in logarithmic form, and I need to go back to an exponential to figure out what x is. So what that says is the exponent on an e, it gets me 3x plus 6 is 5. In other words, e to the 5 is equal to 3x plus 6. And again, remember, e is just a number. It's kind of like, it's a number like pi, and the only way to really write it down is just using the symbol e, okay? Or like square root of 2, you can't really write that number down any other way than square root of 2. You can give me a decimal approximation for it, but you can't write the exact value any other way than square root of 2. So I'm going to continue on just keeping the e in there is what I'm saying. I'm not going to swap that out for its decimal approximation at this point. So let's subtract 6 from both sides. So we get e to the 5th minus 6 is equal to 3x. And then we're going to divide both sides by 3. And if I do that, I get e to the 5 minus 6 divided by 3 is equal to x. Okay, so now that's the exact. And if I want to get back the decimal approximation to that, I would come into my calculator and I go in the numerator. I would go, well, okay, so look, the second function on the ln gives me e to the whatever. So in this case, it's 5. Subtract 6, close the parentheses, divide by 3, and an enter, and there's my decimal approximation. So my decimal approximation is out to 3 places, is 47.471. That's the approximate solution. So let's use the calculator quick to check it. Let's make sure that that worked. Remember that number right there is currently stored in ants. And so I'm just going to use ants for the x. So if I go ln of 3 times ants plus 6, when I hit enter, I better get back a 5. Do the chicken dance because I got it right. Okay? All right, that's as much as I can make out from the question the way it was asked. So I think we'll leave it at that. Hopefully that's going to work. Okay, let's go take a moment. I'm going to go to Canvas. I'm going to go talk about the discussion question. So the big hint this week,